Does it work? Okay, fantastic. Well, thank you, Enrique, and all the other organizers, Mikhail, Lucas. I mean, you did a fantastic job, a great workshop. I have to admit, though, that I feel a little bit out of place because today I will be, after 3 days of quantum computing, I will be talking about a totally different non-quantum approach that we call MEMComputing, computing with and in memory. And it is, in fact, a topological type of computing, which means that it is robust against noise and structural disorder, but again, it's not topological quantum computing. And this is work that I've done with many people, but I acknowledge here a company that Fabio Traversa, who's actually sitting on the back, and we'll talk about later about applications more. He and I co-founded the company, and with lots of imagination, we actually called it MEMComputing Incorporated. The other sponsor is the Center for Magnetic Recording Research at UCSD. And here are a few papers if you're interested. And I will start, however, instead of giving you first the theory behind this computing paradigm, I will start with some results. And in fact, here I start immediately with an NP-complete problem, a very famous one. It's called subset sum problem. And you have, let's say, 5 integers or some integers, and another one, a target integer. And you ask the question, is there a subset that sums to S? If you ask the question, yes, if you want to know yes or no, then this is the decision version where actually we want to know, in fact, if there is a solution, which subset does solve the problem, and this is the search version. Now, we chose this one because there is an easy way to find the hardest possible cases. Remember that when you say that NP-complete problems or even NP-hard are difficult, that is true for the worst case scenarios, not in general. So we actually use this one because it's easy to find the cases where it is really hard. And those are for which the number of elements in the set is equal to the precision, the number of bits that you need to represent each element. In this particular case, there is no pseudo-polynomial or polynomial approach known to us that actually solves this problem efficiently. So the algorithms that we know are exponential, and as I said, I will be talking about a new computing paradigm that is non-quantum, and being non-quantum, we can actually simulate the differential equations of these machines quite efficiently, and so that's what I will show you. At the moment, you don't need to know what these equations are. They are representing currents, voltages, and internal state variables that represent the memory of the actual physical devices that we came up with. But the most important thing that I want to stress immediately is that we map integers into integers. This is fundamental. So these are not analog devices as we're used to because the input and the output are digital. Why it's important? Because we need a finite means. So this way, we need only finite means to read the input and the output. If these were real numbers, we would need an infinite amount of bits to represent a real number, so you would have a fully analog devices that they are difficult to scale up. Instead, if you have mappings between integers and integers, like machines like this one, then it's easy to scale these machines up. Then, as I said, we look for the steady state solutions of these equations, which represent the solutions. So the equilibrium points represent the solutions of the problem. And the results I will show you actually have not been done even by us. We had to engage a third party, an unimpeachable third party, which is the NSF-funded the San Diego Supercomputer Center, which is located at UCSD, but is not part of UCSD. It's actually independent, and the simulations that I will show you have not been done by us, but by them to validate our technology. And what I will show you are results using a MATLAB code running on a single Intel Xeon processor. No optimization, no parallelization. And as I said, just simulations. We haven't built these devices yet. So as I showed before, for the subset sum problem, for the hardest cases, when the number of elements is equal to the precision per element, then the standard approaches explode exponentially. Here at the bottom, you see immediately some difference with our simulations. And in fact, if you push this to about 50 elements, it would take 4.5 years to do it with the standard algorithms, and it took 2 days on a single Xeon processor. You can push it in further, and it would take about more than 2,000 years to do it, versus the 4.5 days using a MATLAB code running on a single processor. Now, this is an NP-complete problem, where, in fact, we can check the solutions quite easily. What about NP-hard problems, where the solution is difficult to check? So these are like finding the optimum in a non-convex landscape, and generally they can be written in a Boolean format like this, where you have variables related to each other by logical ORs. They form clauses, and these clauses are related to each other by AND. This is a conjunctive normal form. Any Boolean formula can be written this way. And if you find an assignment of these variables that is true, such that this formula is true, then this is a satisfiable problem. It goes back to what I showed before. But in general, it's not satisfiable. And so the best you can ask is, what is the maximum number of satisfied clauses? That's why it's called a max set. Or equivalently, minimize the number of unsatisfied clauses. Now, again, for these type of problems, in general, they're called NP-hard, but you have to find those instances where these are really hard. And in fact, there are. Fabio will talk about this later in his talk. There are instances where there is an inapproximability gap, which means there is a distance from the optimum such that if you try to go below that gap, within that gap, then you need exponential resources to actually approximate the optimum. And in fact, we compare with the winners of the MaxSat competition every year. There is a competition where the best teams in the world compete to come up with the best algorithms. And in this particular case, there is an inapproximability gap. And indeed, the best solvers in the world actually explode exponentially, as you can see here. Here are our simulations, actually simulations done by the Supercomputer Center. And we can push it very far because ours scale linearly. In fact, if you extrapolate these things at 2 million variables, this is as a function of variables, this is log scale, then this one would actually take 25,000 orders of magnitude, the age of the universe, if you wanted to actually do 2 million variables. The other one would do actually a little bit better, 2,400 orders of magnitude, the age of the universe. And this took about 2 hours on a single processor using MATLAB. Then lastly, well, before I go in there, we can actually push these things even farther because this is linear. And so we pushed actually to 64 million variables, which is about 1 billion literals, which is huge. And you still see a scalar linear scaling. And in fact, for us, the limitation wasn't even the time, but the memory of the processor where we were simulating our differential equations. At a certain point, we ran out of memory because that processor had 128 gigabytes of shared memory. So it wasn't the time, it was the memory. Of course, you can transform this in C++, parallelize, which means you can push this even further. And finally, since we're in a machine learning type of conference, we actually compared our approach to methods that are available out there. This was done using a restricted Boltzmann machine. As you know, it is very difficult to pre-train these things. Using standard Gibbs sampling, it's contrasted divergence. It's very bad. But D-Wave actually showed a few years back that you can actually improve the pre-training quite a lot by accelerating, actually using much less number of pre-training iterations. But we can actually do the same in terms of number of iterations using our MEMComputing approach in software. This has been done in hardware. This is software. The quality, however, of our solution is even better. And we compare this, and Fabio will show that later, we compare this also with the state-of-the-art supervised learning techniques, and we do much better than that as well. Okay, so there are many more examples. I won't go into those. As I said, Fabio will show more. So I want to answer the question here, how is that possible? How is it possible that a non-quantum machine can actually do what I just showed? And this is only simulations. We haven't even started building these machines yet. So the first question you actually have to ask is, what do we need to actually make a new computing paradigm that is very efficiently? Well, the most important thing, as I said at the beginning, is that the input and the output have to be digital. And this is, in fact, very important because you need to read and write with at most an error that is independent of the size of the machine. This is how these machines are done. The transistors are analog devices, but they're used actually in a way such that they represent ones and zeros with errors that actually do not scale with these machines. If you do this, then you actually have no issues with precision, and the system is scalable. And the other thing we wanted is that we wanted these things to be easy to fabricate with present technology. So with actually devices that we actually can access right now. Now, in computer science, we generally represent the transition function between these integers with algorithms. But why that? Why not using physics to actually do the job? Physical systems are extremely powerful, but if people confound the idea that if I have a physical system, it has to be analog. Analog systems are not scalable. That's not true if you keep the input and the output digital. That's the only thing you need to make these things scalable. And then we use the physics to actually do the job. OK, so in order to do that, we need a very important piece of information, which is what I'm going to show now. And for this, I take as an example the factorization. So suppose you want to factor a number n into p and q, and you write them into binary format where nj, pj, and qj are the zeros and ones that represents those numbers. Now, suppose you know p and q, and you multiply them together, then you have the remainders. This is standard arithmetic, nothing really special. However, if you look closely, these are sums of products of these zeros and ones that represents these numbers. Now, in logical format, the sums can be written as exclusive ORs, and the products can be written as AND, logical AND, which means that the entire product of two numbers of the factoring can be written as a Boolean circuit. This is well known, by the way. It's not something we invented. It's well known in computer science that any essentially arithmetic operation can be written as a Boolean circuit. Any combinatorial optimization problem can be written in Boolean format. This is for the number 35. So you have a Q0 and times P0 plus Q0 times P1, blah, 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 until you get N. So this is what you would do if you actually go from P and Q to get N. What we want is the reverse. But if you want the reverse, which means I give you N and I want P and Q, if you look closely, you see immediately that the gates have to be able to accept inputs not just from above, which is what the standard gates do, but also from below. They have to be terminal agnostic in such a way that actually literally they collect information from any direction of where the signal comes in. This is the key. So what we will do is we take any optimization combinatorial problem, and we write in Boolean format. This is, by the way, not even unique. This is known from mathematicians and computer scientists, so it's not a job we need to do. However, we take those circuits and we replace the standard gates with special gates, which is what I will show you in a moment. Standard gates, as I said, are unidirectional. You give inputs and you get outputs, and that's it. Then you put them together, and the logic is sequential. There is no other way you can do this with the standard logic we are used to. However, if you want to, you can actually design new gates if you allow internal degrees of freedom to let the gate self-organize into the logically consistent solution. I'm not saying that these are one-to-one invertible like Toffoli gates. The only thing we care about is that this is logically consistent irrespective of where the signal comes in. So if this is an AND and this is a 1, 1, it will give me 1. But if I come here with a 1, I want this to be only 1, 1, nothing else. And if I come here with a 0, I want only 3 possibilities, 0, 0, 1, 0, and 0, 1, and nothing else. How does the system recognize or decides in which logically consistent configuration to go? Well, it depends on the initial conditions at which you start, because now we have transformed this problem into a dynamical problem. It's no longer a rigid object, but it's an object that actually dynamically performs this operation. And then we actually put this into a circuit of other self-organizing logic gates, and given an input at appropriate terminals, we actually read the output somewhere, and we let the system self-organize to find the solution for us. Input and output are digital, but the system inside does the job. The physics does the job to actually self-organize into the solution. So if the configuration of this gate is satisfied, there is no dynamics. But if it is not satisfied, the system is dynamically trying to satisfy the solution. How do you realize gates like that? There are two possibilities here. Either you use spatial non-locality, which is very difficult to do actually in classical systems, or you use time non-locality. And that is easy to do because time non-locality is actually a very general feature of dynamical systems. In fact, we know from Kubo theory that any system subject to a perturbation responds with some degree of memory. So we will use time locality, and in fact, you can show that if you have an arbitrary system that has an input and an output y, the response function depends on internal degrees of freedom that give memory, and the input itself, possibly time, and the internal degrees of freedom follow a dynamical equation. Any system, whether it's passive or active, can be written this way. And you have heard probably the system that if I have input and output voltage and currents, these are called memristors. If the current input is charge and voltage, these are called memcapacitor, capacitor with memory, or flux and current, these are meminductors. But in reality, this is much more general. Any physical system subject to a certain perturbation has a generalized response function that actually depends on memory. It has to be. The question is whether that memory is easy to determine or not, but that's the case. And if you actually bias these systems, they will show hysteresis according to the time scales of the memory involved in the system. So these are the systems that we are looking at. And the one that we will use. Now, there are several ways in which you actually can create these gates. And we can create the gates that do exactly what I said before, which is irrespective of where the signal comes in, and then you would have actually the gates self-organize into the logically consistent solution, according, of course, to the initial conditions that you put. So you can build this with memory elements like memristors, as I said before, or in fact, even standard transistors. You don't need any special materials to do this. You can do this in CMOS, fully in CMOS. And so these are, as I said, terminal agnostic, and they're actually bidirectional in the logical sense. Now, if you put this, if you try to implement this using circuits, then all of a sudden you actually have access to fabrication facilities. But the most important thing is that the equations of motions of circuits are of this type, where now you understand what these are. There are the currents, the voltages, the internal states that give memory. But unfortunately, these equations are generally nonlinear. And in fact, according to the initial conditions, they can go to the equilibrium points, which are the solutions of the problem we have designed them to solve, but also limit cycles, periodic solutions. And if you're unlucky, they can actually go into chaos. So we don't want a system like this to go into limit cycles and chaos if we want the system to solve a given problem. Now, you can design these things in a very particular way that mathematicians call, there is an entire field of mathematics of functional analysis, it's called point dissipative systems. And we have designed our logic gates and our logic circuits, self-organized logic circuits, as point dissipative systems. This means that simply the orbits are always bounded, and the system goes always to a global attractor. It means that there is always a compact global attractor in the phase space. Now, it's not easy to actually design these type of things. That's, in fact, the people have tried with neural networks to solve NP-complete problems, for example, but they failed. And the reason we think is precisely because they have not designed them appropriately. And it's an important feature which we actually proved for our systems, because from there we actually prove many more things. In fact, what we prove is that the only equilibrium points are the solutions of the problem we're looking at. The equilibrium points are reached exponentially fast, and the convergence rate scales at most polynomially with size. This is important because if you scale the problem size, we want all the resources, time, space, and energy to scale polynomial, otherwise you would not gain anything. And the other thing that we want is that if there are equilibrium points, then there has to be no limit cycle coexisting with the solutions. And we proved this using function analysis. You can look at these papers. There are about 13 theorems if you're interested. And the last thing we proved is that if there are equilibrium points, then chaos cannot coexist with those equilibrium points. And you can prove this either using functional analysis or even topology. And all hinges on the fact that these systems that we design appropriately are point dissipative. Without that feature, this thing will break down. So it means that when I build these gates and I put them in circuits, then these properties are satisfied. So how do we actually solve a given problem? Well, you start from the problem, let's say a traveling salesman. You write it into a binary representation. This is done by computer scientists or mathematicians. This is well known. But we replace the standard gates with our self-organizing logic gates. And then either you simulate the dynamics or you build them in hardware. Remember, these are classical non-quantum systems. You can actually build them within CMOS. And that's it. And then read the solution. And again, since the input and output are digital, you need only finite means to read the solutions, which means you can scale this very easily. You don't need infinite precision. OK, now you understand what these equations are. Now I write them explicitly, are the equations of voltages, internal state variables, currents of the physical circuits that actually represents the problems that we actually are trying to solve. And as I said before, we implement this in MATLAB, and we look for the steady state solutions, so we know there is no chaos and no limit cycles. Here is the factorization. It's a much bigger version of the circuit I showed you before for 35. This is for 11 bits of 1073. The circles here are the zeros and ones that represent this number. And we literally simulate the physical circuits here. So we have resistors, transistors, all sorts of things. The dots are the inputs and outputs of our gates. There is no distinction anymore between input and output. Black is 1 and white is 0. We represent a logical 1 with plus 1 volt, a logical 0 with minus 1 volt. And we switch on these inputs, and we let the system self-organize. Until it finds the solution. So you see immediately here that there is some, when actually these things flip, so they switch from between 0 and 1, they somehow flip in a correlated way. So it's actually interesting. If you look, in fact, at all the voltages at all the gates, after an initial time where the voltages as a function of time are smooth, all of a sudden you see these spikes, and then they go to the solution always. And if you built this thing in hardware, this would scale as n squared in time, space, and energy. And what about if there are no solutions? Suppose that you try to give a number that is already a prime. Well, you know the scalability, so you know they should stop here, but it will go on and on and on. In fact, we can prove mathematically, rigorously, that this is not chaos, although it looks chaos. It's a periodic solution, possibly with a very long period, which means that practically you don't distinguish it from chaos. And the subset I showed before, you can actually build, and now you understand you can build similar circuits as the factorization, slightly different, of course, and then you will see similar behavior where you have a smooth behavior and then these spikes until the system finds the solution. You can read this actually, as I said, because these are easily because these are digital. This scales quadratically with a number of elements and quadratically with a number of precision, bits per element, if you built this in hardware. Of course, if you simulate these things, it depends on how you simulate. So what is your algorithm to simulate? And in fact, here you see an n to the 4th power because the circuit is square, and we use implicit methods to actually simulate forward the equations of motion. So implicit methods require inversion of matrices, and that's why this thing actually scales so badly. I mean, better than an exponential, but still n to the fourth. And in the case, instead of a max set, the circuit is linear, and we needed only explicit methods to actually solve these things, and that's why you see a linear scalability of the problem. Now, what's really happening, though? I mean, I showed you that we can actually build machines that actually do these type of things. We can actually simulate because these are non-quantum systems, but what is really happening? How is it possible that a non-quantum system can be so efficient, right? This is what we heard. I mean, it looks like there shouldn't be a classical system that does that. It looks like that, as I said before, the gates correlate with each other somehow, arbitrarily far away. Remember that these hard problems are such that when you actually try to solve them, you need to literally flip or change the assignment of variables that are arbitrarily far away. That's why local solvers are bad, right? Because they don't actually explore the entire phase space. And global solvers cannot do that up beyond a certain size. So the key here is these spikes. What are these things? Now, if you look at, let's say, this is factorization, I believe 20 bits. If you look at one of these spikes and look at the correlations of the voltages anywhere in the circuit, these correlations are actually flat. They're not even a scale-free decaying as a power law, but they don't decay at all. So the system is extremely rigid except when actually the voltages are at the edges, of course, because at the edges they don't have the entire bulk to communicate with. So the system becomes literally rigid at one of these spikes. And in fact, if you look carefully, you have spikes, then something smooth, then spikes, smooth, spikes, and so forth. Well, you can actually show what these spikes are from a theoretical point of view. Why? Because equations of motion of this type are what we call 0+1 field theories. And as any field theory, we can actually use a path integral formulation for these theories. And we use exactly the same techniques we use in quantum field theory, but applied only to this type of field theories. And if you actually write the partition function of this path integral formulation, it turns out that the action, the Euclidean action in this case, has a form that is well known to string theories, which is actually of a Witten-type topological field theory. It's a topological sigma model with no gauge fields, and it has a supersymmetry. Now, the supersymmetry we have here is not physical. It is simply mathematical, and it is indeed the exterior derivative on the phase space. But nonetheless, it's very important as a mathematical object because you know that when you have a supersymmetry, you can actually compute much easier certain matrix elements. In fact, if I have a topological field theory of a Witten type, like any action, we know that the system follows the paths that render this action stationary. But in these topological field theories, the actions are stationary over objects that we call in high-energy physics instantons, which are the Euclidean version of tunneling. In fact, they were invented in QCD to compute actually tunneling matrix elements in an easier way by going Wick rotating into Euclidean space and then Wick rotating back into Minkowski space. Here we don't need to do any Wick rotation because we work always in Euclidean space. Instantons are topological objects that connect critical points with different indices. And so now that we have these, we know that these objects are the ones that actually appear in this theory. So the system follows these trajectories, the instantonic trajectories. And we know that the theory is supersymmetric. We can actually compute the matrix elements of these instantons, which means the tunneling between quotes, between the critical points, exactly like, using the localization principle that string theorists use when they actually discuss mirror symmetry. So we can compute these matrix elements exactly in the topological sector, and these are topological invariants, which is important because it means that if the system follows these trajectories, you can do whatever you want. Perturbations by noise, perturbations by structural disorder, the system is robust. Of course, you can change the trajectory, but not the initial and final points. In fact, we actually tested this also numerically by putting noise and structural disorder. And unless you destroy the phase space topology, the system will always find the solution. That's where the topological, why these machines are topological in nature. So what happens? If you actually start from any initial condition, as I said, it doesn't matter because the system will always find will go to a global attractor. These are point dissipative systems. They go first to a critical point that has actually unstable directions that have a magnitude that is much smaller than the stable directions. And once it's in one of those critical points, then it jumps anywhere in this humongous phase space. It tunnels literally in this humongous phase space to another critical point that has less unstable directions, and then to another one that has, again, less unstable directions until it finds the equilibrium final state. Now, since the number of unstable directions is equal to the number of internal state variables, then the number of steps to reach equilibrium can at most grow polynomially, since the number of state variables can grow polynomially with the size of the problem. So this is another demonstration of the polynomial requirements of these machines that we proved using functional analysis, but we can prove it using topological field theory. Okay, so this is, let me see, I think I'm almost done. And this is the key, in fact, to these machines. What happens? At the beginning, the system is smooth. The gates try to satisfy themselves locally, because clearly the connectivity is local. So a gate, they start randomly unsatisfied, right? And the gate will say, well, I need a 1 to satisfy my logical proposition. It tries to get it nearby. And nearby, and the other gates would say, well, if I give you a 1, I will be unsatisfied. But this, all of a sudden, the system becomes rigid, perfectly rigid, so that a gate here in a part of the circuit can actually correlate anywhere in the circuit, so it can actually flip in a correlative fashion with any other gate anywhere in the system. And that's the key to make these machines so powerful. So we have introduced a new class of machines. I haven't talked about the fact that they are universal. But they are. We actually proved this before. They can be built in analog, of course, and we did this as well. But the most important ones are the digital MEM computing machines that I showed you in this talk, because they actually map integers into integers, and we let the physics find the solution. And these are scalable, and they can be built. In fact, you can build them in several ways. In fact, in a way that actually you can actually change the topology on the fly. I won't talk about this. This is interesting from a computing point of view as well, because this is another connection with topology apart from topological quantum computing. This is a classical type of topological computing that uses instantons, so highly non-local objects, in topological sigma models. And I showed the examples of using machine learning and other things. Fabio will show much more, of course. And before concluding, I need to thank my group, the people that actually did the hard work. So Sean, Heike, Jan, and Forrest are my students at UCSD. Fabio Traversa worked with me at UCSD, now is the CTO of our company, and John is the CEO and has been very supportive of our work. With this, I thank you very much for your attention and take any questions.
Yeah, people are already jumping into the questions.
Yeah, thank you. That was very interesting. So I just missed one point. So you have a universal computational machine that can solve NP-complete problems, that's easy to build, and you have a very beautiful interpretation of what's happening. You can show that, you make the string theorists happy. So what do I miss? Science that I know is not like that. It's never easy. It's never gives you everything. Why doesn't that solve now the problems of the world, kind of? I haven't really...
Well, we know that, I can tell you what we can solve. I don't want to solve the world problems, if you're asking that. We just we found a way to actually solve these problems efficiently. That's it. I'm not sure I understand your question. You're asking why not solving the world problems or what?
Hang on, millions of people try to solve NP-complete
why
problems.
it's,
so now you do it, and like, why are you presenting it here? Why are you not presenting it at the biggest computer science conference and everyone like worships you?
Okay. Well,
I think I missed something there. Yeah.
Of course, well, this is pretty recent, so this is recent. And the other thing is that the computer scientists don't understand that a physical machine can actually do this type of things. Remember that when you actually present something like this, right? For a computer scientist, this thing means nothing, because in computer science, what they want is an algorithm, right? Ultimately, if you simulate differential equations, that is an algorithm, but we replace the standard algorithms, combinatorial algorithms, with actually physics, right? That is tough for them to understand at the moment. Because what we were saying is that instead of using a standard algorithm where you literally flip things, right, we transform that algorithm into a physical problem. Then, of course, we simulate those equations, and that becomes an algorithm. But this part is very tough for them to understand at the moment.
So,
I have a couple of questions. The first one is, you were talking about more about self-organization. What do you actually mean when you said it?
Yes.
And maybe the second one, you show this differential equation, and then you apply a method of path integrals to solve it. But it's very general how how can you calculate the integrals?
Okay, so first question is on the self-organizing logic gates, right? What we mean by that is that, here, these are gates that have internal degrees, which in our case we use memory. You could use a spatial non-locality, but we use memory because that's easy to actually, in physical system, easy to build or realize, at least in classical systems. So it means simply that according to the initial condition of the internal state variables, the system has dynamics, right? And so until these things are not satisfied, then this will keep on going. When they are satisfied, they actually are, there is no more dynamics. Now, we build them, we design them in such a way that they will actually try always to satisfy this dynamics. So if you choose an end, for example, you can design this dynamical system so that irrespective of whatever is the input here, they will always try to reach one of the, in this case, 4 consistent, logically consistent points. That's it. You can do that you know, in many ways, but we found a way to actually do that. So this is regarding the question on these gates. So these gates have been designed on purpose with the features that I told you before, which is point dissipative, to actually always find a logically consistent solution. Hamiltonian, you said? Sorry, I didn't hear.
But you always have some classical Hamiltonian.
No. These are not Hamiltonian systems. These are dynamical systems. In fact, dissipative.
What's the difference?
There is a huge difference. Hamiltonian systems are conservative. These are not conservative.
You mean this is very dissipative?
Yes, so that's a huge difference. The other question you ask, how do you compute this? Well, you actually use the standard methods of quantum field theory applied to a field theory. In this case, a 0+1 field theory. So you introduce Lagrange multipliers, Faddeev, Popov, Gauss. You write the path integral using those new set of coordinates, so the fermionic and bosonic coordinates. And then if you write explicitly the action, the partition function, it comes out with an action which has this form, where C is a gauge field and Q is the path integral analog of the exterior derivative. You do the math, you use a differential geometry, essentially. So you just use it. In this case, we don't use this to actually simulate our machines. So we use this just to understand which objects are used by these machines to actually compute. Now, once you know this, then this matrix element can be calculated exactly at the tree level precisely because of the localization principle. That's it.
Yeah, one question. Have you classified the MP problems that you can solve?
What do you mean? We take the problems that we are given by computer scientists, and that's it.
So can you solve any MP problem?
Well, yeah, if you build them there is at least, we know that there is at least a machine, right, that we can actually write, for which we can write, use it for a particular problem. Given a problem, we can actually write the circuit associated to that.
Thank you, Max. Yeah, so very fascinating. So maybe following up with that question, so we know that, so I don't think you're proving that MP equals P, but I think I'm very curious to know, let me see, you had this beautiful physical interpretation. When you analyze, let's say, instances that you can't solve, let's say, or that they take longer time than the typical instance that maybe you're plotting there, do you have an intuition what's happening in dynamics? Maybe the system that is having a hard time to self-organize or fulfill the constraints, or, yeah.
That's a very good point. I think the key is precisely in these spikes that I was showing. In order to actually be able to be efficient, the machine has to become rigid. It's a sort of entanglement, but in a classical sense, right? Without this property, you wouldn't be able to solve these problems. Why? Because those hard problems are precisely where the variables correlate really a long range. That's why I said local solvers cannot do it, right? And you need global solvers, but they explode because they do algorithmic combinatorial approaches. So without this feature of rigidity, so if you don't design them appropriately and they are floppy, it won't work.
Okay, so thanks a lot, Max. There were plenty of questions.